Today we're going to look at some more algebraic approaches to solving of limits in addition to the properties of limits that we learned in the last video. In cases in which you want to solve a limit algebraically, you should always start with trying to figure out the direct substitution. This method works if you have a polynomial or a rational function. And let's say if you want to find the limit as x approaches c, then c must be in the domain of the polynomial and in the domain of the rational function if you have a rational function. If that is true, so if you have a polynomial or rational function in which c is in the domain of that function, then the limit as x approaches c of f of x is equal to f of c. That means we can just directly plug in our c value into our equation. So for our first example, we have the limit as x goes to 2 of 2x squared minus 4x plus 11. Now notice I have a polynomial here, and 2 is in that domain of the polynomial. So all I do is replace every x with 2 and then evaluate. In this case, that will leave me with an answer of 11. In our next example, we have the limit as x goes to -1 of the rational function 2x minus 3 divided by x minus 3. For simplicity, let's change that to 2x plus 3. So let's try direct substitution. Replace every x with -1 and see what we get. On the top, that leaves us with 1 divided by -4, which is -1/4. Okay, let's try one with trig. Now let's just try direct substitution. Replace every x with pi. And I know from my unit circle that cosine of pi is -1. Pi times -1 is -pi. All right, let's look at another trig one. We have the limit as x approaches 0 of sine square of x. So let's rewrite that using our properties. And that would be the limit as x goes 0 of sine of x quantity squared. Now using direct substitution, that's a sine of 0, and then that answer squared. Sine of 0 is 0, and 0 squared is 0. In cases in which direct substitution does not work, you might have to try some more advanced techniques. The first one we're going to look at is called the factor or divide out method. You should use this in cases where you try direct substitution, but it gives you the indeterminate form. That is, you end up with 0 over 0 or infinity over infinity. And those infinities can either be positive or negative. In that case, then you should try to factor or divide out any terms that you can. So looking at our first example in this section, we have the limit as x approaches 2 of x squared minus 4 divided by x minus 2. Direct substitution will give us 0 over 0. So that means I need to try something else. So let's look at x squared minus 4 and factor that to x minus 2 times x plus 2. And then notice I can factor out the x minus 2. This results in a hole in my graph. And I'm left with the limit as x approaches 2 of x plus 2. Now I no longer have a rational function. I have a polynomial in which my function is defined for that polynomial. So I can just do direct substitution. So replacing every x with 2, I end up with 2 plus 2, which is 4. So my limit to this problem is equal to 4. All right, looking at example B, I always want to start with direct substitution. Plugging in 1 into this equation gives us 0 divided by 0. So I have an undetermined form. That means I need to try something else. So we're going to try factoring. X cubed minus 1 is the difference of cubes, which factors to x minus 1 times x squared plus x plus 1 all over x minus 1. Then the x minus 1s and the x minus 1s cancel out, so I no longer had division by 0, which was my problem child, and I have just a polynomial, which is x squared plus x plus 1, which I can solve by direct substitution. So let's just plug in the 1 in place of every x and evaluate. And our answer is 3. Our third technique to algebraically evaluate limits is called the rationalization technique. You use this in cases where you have a radical either in the numerator and the denominator, and the radical is part of a binomial. Also, you need to check that when you try the direct substitution method, you end up with that indeterminate form of 0 divided by 0. In order to use this rationalization technique, it doesn't matter if the radical binomial is in the numerator or the radical binomial is in the denominator. Either one works the same. And what we're going to do is, in order to get rid of that radical, we're going to multiply by its conjugate. And so remember, a conjugate has the same terms, just change the sign in between the two terms. Okay, here's our first example. Now I'm going to start with direct substitution, plugging in the 0 straight into this. I end up with square root of 1 minus 1, which is 0 divided by 0. So I have the undeterminate form. And also I notice I have a binomial at the top and I have a radical. So I'm going to try the rationalization technique. You start by copying down the problem just like it is. Now we're going to multiply by 1, but I'm going to choose this 1 to be the conjugate of our rational binomial. So I'm going to multiply by the square root of x plus 1 divided by the square root of x plus 1 quantity plus 1. Now the term that has the radical we're trying to get rid of, let's go ahead and use our full method and multiply that out. The square and square roots cancel each other out, so I'm just left with x plus 1. The middle terms cancel out, one's plus, one's minus, so I'm just left with minus 1 squared, which is negative 1. On the bottom, I'm not going to bother multiplying this out. You can, but it's just wasted time that you don't need to do. Simplifying this down, 1 minus 1 is equal to 0, so I'm left with just x on the top. And now I can cancel out that x on top and the x on bottom. Leave me with the limit as x goes to 1 of 1 divided by the square root of x plus 1, close square roots, plus 1. And now I'm going to try direct substitution again and see if it works. Plugging in 0 in place of every x, I end up with 1 over the square root of 1 plus 1, which is 1 over 2. So my answer is 1/2. Okay, looking at example B, I'm going to try direct substitution first to see if it works. So we're going to plug in 3 in place of every x. Simplifying that down, I end up with 0 over 0. So I have the undeterminate form, and I notice I have a binomial and I have radicals. So we're going to try the rationalization technique. So I'm going to copy down the problem as it is. And then I'm going to multiply by 1, choosing to write my 1 as the conjugate of my radical term. So that's going to be x plus 2 square root plus the square root of 5. I wrote a minus. Let's change that to a plus. And then we're going to multiply these out. Again, the top didn't have the radical at the beginning, so I don't actually have to multiply that out. I can just write my two products. In the bottom, on the other hand, I do need to multiply out so I can simplify. Multiplying the bottom using our full method, I get x plus 2. The two middle terms cancel out. And then I have the square root of 25, which is just 5. So I have minus 5. Combining like terms in the denominator, we have 2 minus 5, which is going to give us a minus 3. Now I have x minus 3 on the top and x minus 3 as a factor on bottom. So I can cancel those out. Getting rid of our problem child of the division by 0, I now have the limit as x approaches 3 of the square root of x plus 2 plus the square root of 5. And I can do direct substitution. Replacing every x with 3, I end up with simply 2 times the square root of 5. The fourth method of algebraically evaluating limits is called the algebraic techniques method. Again, we're going to use this if we try direct substitution and we end up with that undeterminate form of 0 over 0. But I look at the problem and it's obvious that if I need to do some sort of expanding or some sort of distributive property so that I can simplify the expression algebraically. And that's what I'm going to need to do. Okay, example A is a very good example of one that you're going to use the algebraic technique for. It just kind of screams out that you need to do some algebra. First thing, I tried plugging in every h with 0 and I end up with x squared minus x squared, which is 0 over 0. And so now I'm just going to expand this out. I need to figure out what x plus h quantity squared is. So x plus h quantity squared gives us x squared plus 2 times x times h plus our h squared minus x squared over h. Combining like terms, our x squared minus x squared cancels out, and that leaves with just a 2xh plus h squared over h on top. Notice at the top we have h in common, so let's factor that h out. That gives us h times 2x plus h when I factor that GCF out, divided by h. Oh look, now I have h is a factor at the top and h is a factor at the bottom, so I can cancel it out. I no longer have division by 0, which was our problem child. So that means I can take the limit as h goes to 0 of 2x plus h by simply replacing every h with 0. And that'll give me 2x as an answer. Looking at this example B, if I do direct substitution, the top I'm going to end up with 0 and the bottom I'm going to end up 0. So I have the indeterminate form. And that whole mess at the top just looks like I need to do some sort of algebra. So x plus h quantity squared, as from the last example, we know that's x squared plus 2xh plus h squared. Do the distributive property with the negative 2. And then the distributive property with the negative 1. And then I have divide by h. Looking at the top, let's look at unlike terms. I have a x squared and a negative x squared, which cancel each other out, a negative 2x and a positive 2x, and a positive 1 and negative 1. So all I'm left with in the numerator is 2xh plus h squared minus 2h, and then we have divided by h. Notice every term in the numerator has an h in common, so let's factor out that GCF. Now I can cancel out my h in the top, my h in the bottom, so I no longer have division by 0, which was the problem child here, which means I can now do direct substitution. So I have the limit as h goes to 0 of 2x plus h minus 2. And then doing direct substitution, replacing every h with 0, I end up with an answer of 2x minus 2. The final algebraic method we're going to talk about today is limits involving a trigonometric function. And we're going to use this when we try direct substitution and we end up with that indeterminate form yet again, with 0 over 0 and infinity over infinity. Again, that could be plus or minus infinity. Now, to do this, we need to know a couple of identities we have to have memorized. The first one is we have the limit as x goes to 0 of sine of x over x is equal to 1. The second one is the limit as x goes to 0 of 1 minus cosine of x over x is equal to 0. First example, we have the limit as x goes to 0 of tangent x over x. Using our unit circle, I know the tangent of 0 degrees is 0, and so I have the indeterminate form of 0 over 0, which means I need to do some factoring here, some sort of work. It doesn't fit one of these identities we have memorized, so we're going to do some substitution as using our identities we learned in previous chapter. We're going to have fraction of fraction. That's going to be sine of x divided by cosine times x. We're going to rewrite this so I can use one of the identities above. So I'm going to break this fraction up and have sine of x over x times 1 over cosine of x. Then we can distribute that limit. Limit of a product is a product of its limits. So I have the limit as x goes to 0 of sine of x over x times the limit as x goes to 0, 1 over cosine of x. From our identity above, we know the limit as x approaches 0 of sine of x over x equals 1. And for the second half, I'm just going to substitute in 0. Cosine of 0 degrees is 1. So I have 1 times 1, which is 1. In example B, notice I have a 4x inside the sine function with an x on the outside. So in order to use the identity of sine of x over x equals 1 of the limit, I need to have a 4x in the bottom. So to do this, I want to multiply by 1, choosing my 1 to be 4 over 4. That'll give me 4 times the sine of 4x over 4x. The limit as x goes to 0 of the sine of 4x over 4x is equal to 1, because that's the sine of u over u. Once it's the same thing, that's going to be equal to 1. And then times it by that constant of 4 that I factor out, I get an answer of 4. In example C, I'm going to start by, I notice this is almost my identity for the cosine, except I have that constant of 3. So I want to factor that 3 out, and then I'm going to find the limit as x goes to 0 of 1 minus cosine of x over x, which we know to be 0 from our identity above. And so I simply have 3 times 0, which is 0. Example D of this section, we have cosine of x times tangent of x divided by x. So let's use our tangent identity to replace tangent of x with sine of x over cosine of x. We can cancel out our cosines, and this becomes the limit as x goes to 0 of sine of x over x. Well, that's familiar. That's our identity. So our answer is 1. Example E, we got the limit as x goes to pi over 4 of 1 minus tangent of x divided by sine of x minus cosine of x. Plugging in pi over 4, I get 0 on the top and 0 on the bottom, so direct substitution does not work. So I need to use some sort of algebra. There's different ways that you can do this. I'm going to choose to rewrite my tangent of x as sine over cosine. Simplifying that compound fraction on the top by finding a common denominator of cosine, I end up with cosine minus sine divided by cosine, all divided by sine of x minus cosine of x. Now notice cosine of x minus sine of x is very familiar with sine of x minus cosine of x. So first I'm going to start by rewriting these terms as a negative cosine of x plus sine of x, and then factoring out a negative from the denominator. So I have negative 1 times cosine of x minus sine of x. So I have the same factor on the top and bottom. Okay, when I do a fraction of a fraction, this is going to end up with cosine of x minus sine of x divided by negative cosine of x times cosine of x minus sine of x. Now those products of cosine of x minus sine of x can cancel out from the top and bottom. So I'm left with the limit as x goes to pi over 4 of 1 divided by a negative cosine of x. And now I don't have division by 0, so I can do direct substitution. I recall from my unit circle that cosine of pi over 4 is square root of 2 over 2. Our final answer of negative the square root of 2.